Oh, good afternoon there, everybody, and welcome to today's webinar between GeoEnergy, our partners in the Egyptian region and Middle East and North Africa, and Jennifer Duarte, Leon, who's kindly donating her time and services today to run through what's new in IP 2019 for you. As well as an introduction, we'll be taking questions throughout the duration of the webinar. And we're going to split that into 3 sections. So for the first 45 minutes, we'll be showing you what's new in IP 2019, and that should last about 45 minutes. We'll be then aiming to have a 2 to 3 minute break, just for everybody to have a relaxation break, get a drink and come back. And then we'll be moving into Get More and Do More with IP Advanced. Again, that session will last about another 45 minutes. And then we'll have a 2 or 3 minute break again. And followed by that will be a Q&A lasting about 10 to 20 minutes. And to help me with that Q&A, if you could please post any questions on the questions window. I'll be picking those up during the webinar. And if you have any issues, please just post those in the chat window and I'll try to address those as we go along. By way of an introduction, Jennifer is an experienced geoscientist, a technical sales consultant for us here at Lloyd's Registered Digital Products, and is a specialist and experience in petrophysics, our IP, which is interactive petrophysics, and IC software, working alongside petrophysicists and geologists to provide technical advice regarding IP and IC software to refine current workflows and develop new ones. In Jennifer's spare time, she volunteers as chapter secretary of the SPWLA in Abu Dhabi, which is a non-for-profit organization dedicated to the advancement of petrophysics. Alongside Jennifer today will be the operations manager from GeoEnergy, Mohamed Hataba. Mohamed is an experienced geophysicist with a demonstrable history of working in the oil industry. So you're in safe and capable hands today. We want to make this enjoyable, but if you can keep yourselves on mute and just post any questions to me, I'm going to hand you over now to Mohamed. Thank you.
Good afternoon, everybody. Gentlemen, I am Mohamed Hataba, the operation manager for GeoEnergy. I would like to thank you for accepting and joining our webinar with Synergy today. GeoEnergy, in brief, is one of the leading professional petroleum services provider in Egypt and Africa and MENA region, specialized in data management, G&G software, training, and consulting services. GeoEnergy also is a sole agent for Synergy products, and we will be pleased to contact you and receive all your inquiries and clarifications about IP and IC through our business development team, represented by Ibrahim Al-Khouli, our BDM, and the operation team. Finally, I hope you enjoy the webinar today, and now I will pass the word to Jennifer to start. Please, Jennifer.
Oh, thank you, Mohamed and Rich, for the introduction, and hello to everyone that have joined today's webinar. Just to recap on the agenda of today, I'll start off with showing you what's new in IP 2019, and then I'll move on into and show you some of the advanced module, including the IP mineral solver, and the curve prediction modules, and the image analysis module. Then I'll give you a quick introduction to IC, which is our sister product, and how you can use IC to integrate it with your IP analysis. So the focus for today will be to show the features in 4.6. This is our latest release version, and this version also includes functionality that were added in 4.4 and 4.5. You can see here how we have added a lot of functionality in 4.4 and 4.5. For instance, in 4.5, we added a new NMR light hydrocarbon correction that it pretty much takes into account about the low hydrocarbon index and then low T1 effect. This is based on a solution of density porosity and NMR porosity. In 4.5, you can see that we added a lot of upgrades to it everyday workflow. We added new tools to manipulate the data, such as star plots, where you could actually visualize the statistics and the average value of phase curve and electrical logs. So in this diagram, you can see how we're displaying the data in a star plot, and you're able to see those average values for those phase curves. So the color actually represents each of the phases, and you can see them all the phases, combine them together, or you can see them individually representing that average value. You could also see the data in a spectral plot, which is what you see here down the bottom. And it pretty much displayed the same data that the star plot is displaying, but in a spectral matter. So now let's see what's in IP 2019. I'll start off with the modules and the new functionality that we added. Then I move on into the module upgrades to the existing modules, and then I'll show you what's coming soon. This more or less will take about 30 to 45 minutes. The new Curve Auto Edit module allows you to repair logs that's been affected by a washout. Now, the default setup is to repair using density log, the sonic log, your neutron log, and the PU log. It does this by creating a multilinear regression for each logs using others as inputs. Now, to make the module more robust, we added the gamma rate and the resistivity log. And this is because you're always going to find a gamma rate and resistivity log in all your wells. And these are the logs that are also less affected by a washout. But what drives the whole process, or where to repair, are these crossplot flags that you see here. And you do that by actually using the crossplot functionality in IP. So in here, we're looking at a density neutron crossplot, where we have highlighted where we think is the good data by creating an area. Once you create an area, you could then actually create a curve from that area and then use those as an input into your input model. Once you run the module, then you get the result plots. So in here, you can see from left to right, we were looking at the good logs that we added, the gamma ray, the resistivity log, and then as well as that, you also see the crossplot flags that were built. So in here, we could see where we have the good data, and then in here in this interval, we could see where we have flag where the bad data is. This tracks that you see in here are the logs that were used in the input model with the multilinear regression. So it's a good way for you to actually QC the multilinear regression prediction that was done for the inputs logs. So in here, we see the density, multilinear regression, the neutron, the sonic, and the PEF. And then in here, you can see how the multilinear regression actually came out really good when we have the good data, but then it wasn't really good when you are looking at the bad data, or when you're looking at the washout area, which is this particular interval. Now, once you run the module, you get this last two tracks as well that shows the logs that you use as an input, but also the enhanced logs that were created after the multilinear regression was run. And you could see in this particular area where we have the washout, where the logs are actually being enhanced compared to the raw data. The multilinear regression might not be good if you have a significant difference in lithology. So for example, if you're dealing with a major lift boundaries and you're dealing with a carbonate sequence or above or below a clastic sequence, in that case, what you will have to do is actually zone it in two different zones to reflect where you have your carbonate sequence and where you have your clastic sequence. And what this is going to do is going to create a multilinear regression for each of your zone once you zone it. And then in here, we're looking at the same data, but we are looking at it at a different scale. And you can see the interval that we have the washout area again, how the log has been enhanced after the module was run. T-tool parameters, it's another enhancement that we added to IP 2019, and it's actually a significant upgrade. And it does what it says. It allows you to tilt any interactive parameter in IP. The reason you might want to use this is if you probably want to capture, let's say, for example, a wet clay compaction trend in the density log. So when you do this, you could come into say, for example, the volume of, when you calculate the volume of clay, you will have your parameter tabs and you have your neutron density. So if you want to capture that wet clay compaction trend, you could come in here and then just add a curve, right, or a value. And the curve can actually be added if you run a user formula or any script, or you could actually use the other option, which is the tilter parameter, to actually reflect that compaction. So in this particular example, we're actually looking at a zone number 2, where we have calculated the volume of clay. And then you can see here on this graph, we have the gamma ray log. And then the red line is actually the gamma ray clean. And the green one is the gamma ray clay. And then to make this interactivity, there's an option on top of the template that if you click on it, now it allows you to actually tilt that parameter. So the conventional way was, if you looked at it as zone number 1, will be to actually move this line right or left, right? And that will create a one particular value. But with the tilt parameter, it's going to create 2 separate values where you pick the first pick and then where you pick the second one. Now in this zone number 2, we're dealing with a sand. It's a sand zone, and then this top sand here is just as clean as the bottom one right here. So you want to pick this parameter to reflect this. And once you tilted this parameter, you see that reflected on the parameters and the distribution window. So you see that here in zone number 2, where instead of having one value, we now have 2. 38.5 represents the value that I picked here, and the 58 represents the one that I pick on the bottom. Now you also see that reflected on the cross plots. So when you look at the density neutral cross plot, when you're picking your clay line, in there, once you make that tilted parameter, you will now then see a cross indicating that that's a tilted parameter. You would also see it on the histograms if you're looking at the gamma ray log, and then you're picking your gamma ray clean and your gamma ray clay. There's now an arrow indicating that that's a tilted parameter. You can also use the tilted parameters when you deal it on a logarithmic track. For example, if you're dealing with an NMR log. So if you want to pick your T2 cutoff on the NMR log in this track, then you could make the tilted parameter available and then pick the top bottom and the bottom value. Now it might be an example might be whenever you're dealing with a carbonate channel sand sequence, right? Then you might want to reflect that maybe on the top is when you have your carbonate, and then on the bottom is just channel sand. So then you can make a tilted parameter, and that will be reflected on that zone number 2, where you now see an LG saying that that's a logarithmic. 90 is the value that was picked on the top, and then 14.8 is the value that was picked on the bottom. Global parameters, it's another enhancement that we added to IP 2019, and it provides a streamlined method for users to run a single parameter set on multiple wells. The parameters exist in one centralized place, and just purely is for simplified management. So what are they for? Say, for example, if you have done an interpretation in one of the wells and you want to apply it to hundreds of wells. Or it could be the case that you have the parameters in a spreadsheet that contain all the parameters. Or it might be the case that your wells have not the same stratigraphic column. So the system behind it works out which wells need the parameter for each individual zone. This is something that the standard batch run module wouldn't handle. So you can now see an option under the multi-well menu, and in there's now 3 new modules that correspond to the global parameters. So where are they stored? Where are these parameters stored? They're actually stored at the project level rather than the well level. And there are two options to actually create these parameters. One option is by using any of the existing standard zonal parameter sets, which is this picture that you see in here. So when we're calculating the volume of clay, in there is an option where you see your parameters, where you have your zones, gamma ray, and neutron resistivity parameters. And if you click on low save parameter set, this will open up a window where it now has a new option called save to global file and load from global file. Or the other option is to actually create them by using the global parameter set editor menu. And this will take you step by step on how to create those parameters in case you don't have any interpretation done. So you will need to choose the parameter step type, the global parameter set file name, and if you want to use your picks, then that's optional, but it's used to for selecting the zone tops and the bottoms. So once you have a global parameter set, it's really easy to update these parameters. One way is that if you actually looking at the the parameters tab. In there, you will notice that, okay, if you look at the zones, if you right click on it, there's an option for change, add an update zone in a global parameter set. That's if the case if you want to actually update a zone. But what if the case that you want to update a value, a parameter value? Now, again, in the parameters tab, if you right click on it, there's an option called change the parameter value in the global parameter sets. And then that way you could change and update the global parameters. Multi-well batch plotting is another feature that we added that can also save you a lot of time if you're actually working with a large database. Say, for example, if you have already built your CPI in one of your wells and you want to propagate this to the rest of the wells that you have on your field. So in the past, it was a little time consuming going one by one. So now with this well batch plotting, you could create one template, your one CPI for one of your wells, and then use the modules to select the wells. Then you have to also choose where you want to output to. So you could output it to a printer or a graphic file. It could be output as a PDF file or a GPG, and then you need to choose the plot format that you have built to then propagate it to the rest of the wells. And then once you run it, then that plot will be created for the rest of the wells that you selected. Now this option is under the multi-well menu, and then you'll notice that now there's a menu called multi-well batch log plotting. And honestly, this can save a lot of hours of individual well plotting instead of going one by one. Another piece of news, in IP 2019, we came into agreement with IHS Market to try to bring our IP product and their Kingdom product closer together. So to do this, we created a Kingdom connector within IP. It is available under the export data menu, and then you'll notice that in there there's a Kingdom option, and you could transfer data between IP to Kingdom or Kingdom to IP. The data that you could transfer are things like well data, logs, and any electrical logs, formation tabs. And once the connection is made, it gets a summary of the data that is going to be transferred. So again, you could go from IP to Kingdom or from Kingdom to IP. So now let's have a look at the module upgrades. We have also made upgrades to the current modules. There were around 9 modules, some significant upgrades. So let's take a look at those. Well maps, it has a significant upgrade when you actually display the wells. You're probably aware that we have a module to see where the wells are actually positioned across the field. You could do that by using well header information. So if you have the latitude and longitude information and the header, you could come then into the well maps. I displayed those wells. Now, previously, all the circles that you see here representing the wells were gray. You can now see that they're more colorful, and that's because we added the ability to color wells based on the wet list, which you could load from this option. Now, wet list is actually a way to group your wells. So say, for example, if your field, you have a block A, block B, or block C, or area 1, area 2, or area 3. Now, you could use the wet list to actually group those wells and then display them in here by colors. So the purple colors in here represent the wells that are on my area 1 or my block 1. The blue colors here represent the ones that the wells that are on my area 2, and then the pink ones represent the ones that are on my area 3. But you will also notice that there are certain wells that have different colors, more than one color. That's because those wells are in more than one well list. And I mean, the well lists are really easy to create. You could create them from either of the multi-well modules or within the well maps as well. The porosity and water saturation module in 2019 had an enhancement on to where the interactivity to the glacial ratio parameter. And that's the parameter that you see here on the parameters tab. Now, in the past, it was only a manual. So if you want to edit this parameter, you will come in here and then just type the value for it. But in IP 2019, we made it interactively. So you see that when you're actually looking at the density neutron plot, and then in there, now you could see this red dot representing that glacial ratio parameter. You would also see the interactivity when you're looking at the porosity map versus the porosity crossplot versus the V-clay. So there's one for porosity affected and one for porosity total. And then you could see the interactivity parameter there. Now, if you follow the V-clay workflow, this parameter, the glacial ratio, is used to produce the option to output a V-shaped clay. Because you might want to plot your final CPI in terms of V-shell rather than a V-clay. So this parameter is the fraction of the clay that's seen in 100% shell, and it's used to compare the clay parameters to shell parameters or inverse, depending on the workflow that you're following. The capillary pressure loader and the saturation high module has been upgraded so that you can now copy and paste multiple spreadsheets from Excel. So in the past, it was a little bit cumbersome when you were dealing with a lot of capillary pressure points. If you're dealing with a lot of MICP points, centrifuge plates, or porous plates, it was cumbersome in a way that on how to load those blocks, because you will have to go one by one and copy and paste. Now with this upgrade, you could just simply, if you're dealing with multiple spreadsheets that have multiple blocks, you could use the load from Excel option, and this will allow you to just point to Excel and then map the columns of, let's say, for example, the well name, or where you have the depth or the porosity value for that particular plot, or the permeability, or even the capillary pressure data, or the saturation data. You could just simply map it and then view it so that when you click on load and update, it will load all the multiple sheets in just one go, or all the multiple tabs in just one go as well from the spreadsheet. The saturation high module has some upgrades on to the methods for calculate closure correction. We added new methods to apply this correction. So if you look at it here at a cross plot, this is a capillary pressure closure correction plot where we're looking at a capillary pressure data, and the blue curve here represents the raw data, and then the gray one, it represents the corrected one, and the closure point is this that you see in here. Now, in the past, the default method to correct this closure correction was what we call a shift method. But now in this version, we added more options. So the shift method, what it does, it takes it shifts the whole PCSW plot value by a fixed amount. And what it's going to do is actually, so in here, when we're looking at this curve, it's roughly 80%, where when we apply the closure correction point, is going to shift, let's say this point to there, this point to there, and the closure point is going to be here. The proportional method is one of the new methods that we added to it, and it takes the same saturation value and divides the saturation plot value by that value. So in other words, it stretches the curves. So you will see your closure correction point there. The crop method it cuts the plot at that point and at that value, and the extrapolate method, it's similar to the craft method, but now what it's going to do is actually going to extrapolate the last gradient and takes the closure correction point straight out. There is new features to the cement evaluation module, and there is ability to import existing well diagrams. So inside the cement evaluation module, there are some options to add the completion data. So if you have your casing or your cement data. Now, if you're familiarized with the well diagram manager under the edit menu, this also allows you to do that, and it allows you to create a well schematic diagram like what you see in here. Now, with the new update, it allows you to actually import the well diagram that was actually built on the diagram manager and actually bring this data in and then display the casing and the cement data. There's also new radial tools. So we added the Hunting Teton RIB. And there's also a new advanced tool workflow option for when you're dealing with light cements. So these are the tools from Schlumberger, the isolation scanner, and the Baker Hughes integrity explorer. And these tools give two measurements to calculate the bond between the casing and the cement. So here we have the impedancy and the flexural measurements. So what you could then do is actually interpret those individually, or you could combine those two methods and combine them. So in this particular example, it's an isolation scanner from Schlumberger. And then you can see here on this track where we have the impedancy image. And you see that it's struggling to see the bond in this section. When you look at the flexural image, which is in this track, you can see that showing a stronger bond. But when you actually combine them together, the flexural and the impedancy, the final image, it kind of like shows the best of the two maps. So it powers the results, and ultimately it shows which zones have passed or not. So the green colors actually are the zones that pass in that particular area, in that particular zone. The acoustic waveform processing has some enhancement to how you actually display the data. So there is a manual first break tool, which is the plot that you see here, and allows you to repick first arrival and waveform and improve your delta T calculation. There's also some new editing tools. So this handy little thing that you see here, you can display it on the top of your plot as you are editing the data, and you could select different methods. So there's a rectangle. So when you're picking your compressional, you could either select, let's say, the rectangle method and create a rectangle on the plot. There's also a new outputs to assist for a fracture identification, and this is purely when you do an assemblage calculation. There's an enhancement to the assemblage processing, which result on a smooth image and improved results. And there's also a way to custom the processing range input. And it's normally when you're picking the frequency filter range on the display that you're going to process. So we have done a lot of work in our image analysis module, and there is a section later that I'm going to be cover, which I will talk about the functionality. But just to summarize, in IP 2019, we added a new image correction called an image flattening. And what it does, it's a technique that is used to remove the effect of borehole inclination and deep embeds from a borehole image. So in this example here, we started off with a corrected FMI image, and then we have a pixel in here, the last track, detailing the local regional deep. Now you get your resultant flattened image that can be seen here in this track, and then there is a on track number 6, you could show a comparison of the average conductivity for the regional and the flattened image. So the more accurate the peaks are, the flatter the resultant image will be, which is what you see in this image. This is useful when you're actually doing image calibration or secondary porosity calculations. There is a new data types. So there is a breakout propeller data type, and it helps when you're picking a breakout. So at this point over here, it has the point and the deep style, like a propeller, and it looks that one dip, but it will count as 2. So you can see that reflected here when it's picking the breakout. There's also a new deep import from file. And this allows you to import data either from IP or a third-party source. We also added an ability to edit pics straight from a StereoNet. So if you want to edit or delete data types, you could do it from you can now do it from the StereoNets. And the mechanism is to actually select the points that you want to edit. So in this case, the pink color represents that multiple data points that I want to edit, and then here are the blue ones, and then the light blue represents that data type as well. So you pretty much have to select the points, and then you could delete or edit, and then you could set the quality, the comments on the lithology, and then the descriptions for each one of them. Other new features, we added more templates to the tool types. So there's a Halliburton HFLB. If you're exporting the data from TechLog, we have a new template for a Baker Earth and a neighbor's frac view. There's also an ability to switch truncation direction easily from the image. So in here, if you right click on the image, there's an option that says truncation, and then now you're able to select if you want to do if you want to truncate the first selection uphole or downhole. There's also the ability to display depth range and the legend in the StereoNets and ROSPLAT, which is what you see in here. You can now see the legend. And there is a data type template files can now be supported through the corporate search folders. For those of you who are using Principal Component module, you will notice an upgrade on the Output tab. And we just added the eigenvectors and the eigenvalues. So previously, these were only available in a text report. So looking at the eigenvectors and the values, you can see the contribution of each of the input curves that has on each of the principal components. So in here, you could see how we have 4 different principal component curves, and it shows us the eigenvalue and the eigenvector for each of the logs that we use as part of the input for the model. So in this case, it's using the gamma ray, the density, the neutron, and the DT. And that is also showing us the percentage of variability for that particular curve. There is also a new correlation tab, and this will show a visual representation of the influence of each log to each principal component. So those are actually the eigenvectors and the eigenvalues that were on the output tab. You can now see them here represented graphically. So if we look at this example, is using again the gamma ray, the density, the neutron, and the sonic, and then it has calculated 4 principal components, and then this right over here, the quality of representation represents the weighting that each log has on that particular principal component. So in here you see you have your principal component 1, 2, 3, and 4, and then it's showing us the logs, and the circle actually represents the weighting or the influence of each log to that principal component. So we could see that the gamma ray, because it has the bigger circle, it has more influence on principal component 1, and the sonic, because it has a small circle, it has a less influence on the principal component 1. Unlike if you look at the principal component 2, the gamma ray is actually the one that has less weighting or less influence. And then the sonic is the one that has a more influence on that particular principal component. And you could also see that represented on a PCA correlation cross plot, which is what you see in here. So for, X and Y, we have a PC1. For the X-axis is the PC1 curve, and the Y-axis is the PCA2. And then it's also showing us those eigenvectors values for those logs that we use on the model. And ideally, the farther the value is from the middle, the more influence that log will have. You can also see them you can also visualize them from different wells as well, rather than just do it in a single well mode. You could visualize them and see, okay, this is how I look in my well 1, my well 2, and my well 3. And this is useful when you want to visualize the statistical difference between the wells and see if there's any correlation between the logs. Contingency table module has now a calibration data option. Normally, you will use this module if you want to compare 2 sets of facies when you're doing a rock typing. Now, one limitation was that you must have the same number of values of the curves you're comparing. Now, with this calibrated data option, if you have it on, you're saying that both of the curves that you're comparing have the same number of facies. But if you have it off, now you're saying that the curves that you're comparing, they have a different number of facies. So, for example, when you're comparing facies versus the hydraulic flow units. And here's just an example on when we're comparing 2 curves with a different values in each of them. So in here we have the facies curve where it has 7 data points, and then in here we have the hydraulic flow units that only has 4 data points on it. Our mineral solver module has an upgrade on when you make the plot. So you could now discriminate a model when you're plotting that model. So in here, it's a carbonate model. It has some limestone cores, dolomite, clay, and then it has the fluids. So if you use our mineral solver model, you are aware that you can build multiple modules and then mix the models based on certain discriminators. So when you're looking at the results, you can then now discriminate that model to the interval, and which is what you see here now, and that I have discriminated that based on that. So what it does, it allows you to help you focus on the intervals that actually matter. So if you want to target just your reservoir zone, then you could discriminate that so that you could then plot it here, which is the struct that you see there. Also, in the mineral solver, we have added a new outputs equation. So when you build in your model, on the equations option, there's now a new options to output the density hydrocarbon correction, the neutron hydrocarbon correction, and the sonic hydrocarbon correction, which is the same logic that we applied on the outputs to when you're running the PSW module, the porosity and water saturation. So what's coming soon? IP 2021 will be released next year. So I just thought on showing some slides of what to expect. There's going to be a new displays for data and the plots. We're going to have a pie chart and rows plots. So in here, you're looking at a pie chart with a lithology curve that actually represent different phases. So you could have it as a standalone, or you could actually add it to a template where you're looking at the logs. And then correlated with the logs. There is the same case as when you're doing rows plots. So in here, we're looking at a rows plot where we have different zones, and the colors represent the different zones there. So there's a heavy heterophore fration, and then you could visualize them as a standalone, or you could also add those to the log plot, which is what you see in here. The production login will have some updates on the tools. So we'll add a new tool from Schlumberger, which is the FSI. So this tool is mostly used when you're dealing with deviated and horizontal wells. You might remember that in IP 2018, we introduced our first advanced array tool workflow using the GE Maps tool. Now for these tools, the sensor displays around the circumference. For FSI, it's different as the sensor are actually vertical, displayed down the borehole. And it uses the depth and the ghost sensor to make a three-phase downhole interpretation. And this is some of the displays that, that the FSI will show. And lastly, there's going to be a new casing inspection module. It's now in development, and it's going to be using a multi-finger imaging tool and the ultrasonic logging tools. So you could display the data on the log plot with interactivity on the cross sections, which is what you see here. And you could edit and remove bad data, or you could centralize or normalize the data and do color recognition. And you could also run a statistics of wear and buildups, and it will create a report join by join conditions. So this brings us to the end of our first section on what's new in IP 2019. So we're going to have about 3 minutes break before we start with the next section.
Yeah. No, thank you very much. That was excellent. Thank you, Jennifer. We'll look forward to part two. Should we make it 5 minutes? Is that okay, Jennifer?
Yeah, that's fine. Yeah, we do
I think you bought us 2 minutes there. So if should we say it comes back for 10 to the hour? Should we do it that way?
That's fine. Yeah.
Perfect. So we'll all stay. So we'll start again at 10 to the hour. And thank you. All go and have a break, get a drink, and come back in just over or just under 7 minutes. Thank you. Hello again, everybody. Part 2 is get more and do more with IP advanced modules. Hand over to Jennifer. Thank you.
Oh, thank you, Rich. So this section will cover some of the IP advanced modules. A little of a background on the theme of this section. So most of you will know IP as a petrophysics tool, but over the years, you have seen that we have moved to different disciplines. You saw today that during the What's New section, we have added a lot of enhancement to our different modules that we have in IP. So we have the IP geology modules that include the image analysis, rock typing. There is the IP wells that includes the geosteering, cement evaluation, pore pressure. There's also the IP geophysics that has the rough fixes and the curve prediction and the acoustic waveform. But there's also the IP formation evaluation that includes the mineral solver, Monte Carlo analysis, curve prediction, and rock typing. If you looked at an IP reservoir, we have the saturation high modules, formation testing, production logging, and hydraulic flow units. And then lastly, we have the IP geomechanics that includes if you want to do a complete wellbore stability study and a pore pressure prediction, or if you're dealing with sand failure, there's a sand pit 3D. So with this next section, it's just to give you an awareness on the functionality behind some of our advanced modules. I won't be able to go too much in detail due to the time, but in case you want to have a look at more in depth, or like a live demo of the modules that we're going to show, you could let the team know, and they will be able to actually discuss it and schedule a demo section later. So as far as the agenda for this section, I'll talk about our IP's mineral solver, which is our probabilistic approach for porosity, water saturation, and mineralogy. And then I'll talk about the curve prediction modules that we have in IP. And then I'll finish up with the IP image analysis. So if you're working in a more complex formation, or if you're dealing with carbonates, our mineral solver is a probabilistic, non-deterministic petrophysics solution for complex formation. Now, before we understand what a non-deterministic solution is, we must understand what a deterministic solution is, which is what the PSW module in IP does. It is a deterministic solution because you're dealing with two equations. You have two equations that you want to solve for. So if you look at the neutral density porosity, you start with the density neutron log, right, to solve for porosity or row matrix. And then you use your RT and RXO to solve for water saturation and XXO. And then the process iterated until it converges to then find a final solution. So this is what we call a deterministic solution, where you have two equations for two variables. So our IP mineral solver is a non-deterministic solution, and a non-deterministic interpretation means that there does not have to be the same number of equations as variables. There could be more if you run the module overdetermined, or it could be less if you run the module underdetermined. There's also not one unique solution, and the data that you're adding to the model is considered to contain some uncertainty, which the log measurements certainly do. So they're not treated as what we call absolute values, like how we do in a deterministic solution. So what IP is going to try to do, it's going to attempt to solve the system of equations to find the most probable result for each layer in the well. Traditionally, this is also called a probabilistic approach. And we could use a non-deterministic or probabilistic approach if you want to account for a log uncertainty. But there's also the case that if you're dealing with a complex mineralogy, for example, volcanic clastics, or weather basement, or mutual evaporites, or salt plug porosity, you could use the mineral solver to do that, to build a model for that. Or there could be the case that if you want to solve multiple clay minerals. So instead of actually treat all your clay minerals as one, for example, if you want to break out your X-metite or your E-lite minerals, you build a model so you could add those X-metite and E-lite to the model rather than just treat them as a clay minerals. If you want to also incorporate more log data, so if you have any gamma ray spectroscopy data, then you could use the mineral solver to do that. Or just to account for the fact that the porosity logs have a different depth of investigation. So for example, the density and the neutron, they don't log the same zone. So the mineral solver is used to solve for mineralogy, porosity, and fluid saturation. The user needs to enter a mineral or rock model for the formation, which is what you see in here. So on the right side, we're looking at the minerals for the model. We have the calcite minerals, quartz, dolomite, clay, and then the fluids. And then there also needs to be the tools to be used to calculate those. So for that, we have equations like the density, neutron, sonic, volumetric cross-section, and the gamma rate. And the program is going to try to solve the system of the equation to find the most probable result at each level. So the equations solved are both linear and nonlinear, and the nonlinear equations are solved iteratively. So we could take a look at the neutron log. That is a nonlinear equation, as the matrix endpoint is dependent on the porosity. And to solve for porosity, you must calculate the matrix endpoints. And to calculate the matrix endpoints, you must know the porosity. So traditionally, like I mentioned before, it's called also a probabilistic or a stochastic interpretation. But although it can just be considered a non-deterministic interpretation. So the porosity is solved as the sum of the defined fluids in the model. And once the porosity has been determined, mineral solver is going to try to compute the saturations, XXO and water saturation. As we know, saturation equations are nonlinear. So the default and recommended method in IP is to solve these equations outside of the model. We do this by adding the RT and the RXO logs in the EPON tab that you see in here. So we have the input curves, and then you'll notice that there's an RT and RXO option. And these are then solved in an iterative loop method, which is then a similar method that we use in the PSW module, in the porosity and water saturation module. So if you notice, the resistivity logs are used in the solver, even if they're not defined in the model as resistivity equation. They've just been treated outside of the model. The mineral solver comprises the mineral solver pre-processing and the mineral solver model interface. Now, with the pre-processing part, it's a step that if you don't have to use it, then you don't have to use it, but it just depends on what are the calculations that you need. So the pre-processing allows you to calculate a volumetric cross-section. Now, normally you get the volumetric cross-section from the vendor, right? They will give you a volumetric cross-section, but you could use this pre-processing in case you want to create a new curve using the density or the PEF curve, or if you just want to QC the one that the vendor provided to you. And it's just an equation so the volumetric cross-section is just an equation that is using the density logs times the PEF, and that will give you the volumetric cross-section U. There's also a calculation for conductivity in case you want to use your saturations inside the model. And then for that, you actually use the inverse. So we're using the resistivities curve as an input to then get the conductivities. The pre-processing tool also has an option for when you're actually dealing with XRD data. Normally, this core analysis data is usually provided by core laboratories in a weight percentage of the dry fraction of the rock. So in IP, they have to be in a volume rather than a dry weight. So there must be a conversion that going from a dry weight to a volume conversion. and that's what this option allows you to do. So you will need the weight curve and percentage, the mineral density for each of the minerals, and then you will also need a grain density, and then the porosity curve. So it does the calculation to then come up with the volume fracture for that particular mineral. So the mineral solver interface, when it comes to what is the typical workflow, now I'm going to describe what will be a typical workflow inside the model. So if we take an example like a carbonate oil reservoir, this could include a limestone, which is what you see here, dolomite, there could be some anhydrite, also there could be some clay, and then apart from that, there's also the fluids. Notice that I didn't add a shale here because shale is not a mineral, and it still is not a mineral. So that's why I added clay to it. So once you pick the minerals, what this is going to do is actually try to come out with some endpoints, mineral endpoints, which is what you see down here. Apart from getting the minerals, you also need the equations, the tools equations. And these are the tools that are actually available in the well. So you could use the equations like the density, the neutron, the sonic, volumetric cross section, which is the it's using the density times the PF and the gamma ray log. Now this is not just only limited to these equations. You will notice here on the right side that I have listed all the rest of the equations that we also have available. So if you have any EPT data or any case-hole data like the sigma curve, you could also use that and then build a model based on that. Or if you have any ECS or any TOC curve or any grain density, you could use those equations to actually add them to the model. But this is just showing a just really simple model with just these minerals and these equations. I mentioned about the endpoints, which are the ones that actually get populated when you're picking your minerals. So you could see them in here. So for example, we have the dolomite, and then there's some endpoints there. So you see some values. There's a density value, there's a neutron value, depending on the equations that you added. Now these are actually they're pre-defaulted in the solver, and then you could see the values, the endpoints values that we use by default. Now, in case there's a value that you want to actually edit, you could come into this file and then edit those values. So notice that in here we have the calcite value, limestone value for density as being a 2.71 because we know those values. There's a 2.65 for quartz. So once you add those to the model, this will automatically be populated based on this endpoints that we have by default. These endpoints can also be picked or adjusted by using a cross plots, and this is what you see in here. So if we look at a neutron density plot, we're looking at where the clay points fall, and then if we're looking at the volumetric cross section and the sonic cross plot, you'll notice where you have the clay point, where you have the calcite point, dolomite, and quartz, and you could interactively move those points to where you think the course will be, the dolomite, the dolomites should be, and the calcite. And as you move this, then it will actually update the grading of the minerals. There's also a parameter that needs to be added to when you're building your model. Apart from adding the minerals, like I mentioned, and the equations, there's something called confidence. And this is the relative importance of one of the equations to another. It is expressed in log units. So for example, if we're looking at the density, it has a value of 0.02. And here we're saying that the density has a plus or minus 0.02 grams per cc. So if you're dealing with, say, for example, a bad hole, this confidence value is less accurate, and the value should be increased to, for example, maybe 0.04 grams per cc. By doing that, we're actually decreasing its weighting of that particular lock, of in this case, the density lock. So the confidence value is a weighting of the locks in the model. And once you have that defined, then you could run the model. And then it'll give you this output. It'll show you the solution. So if you look at it from left to right, calculates the saturation and the porosity, and then it also gives you a combined mineral model. Apart from that, you also get an error, a total error track, and it's normally the normalized total error curve. If the error values are greater than 1.0, they're displayed in red in this track, and you can use this as a way to visualize on how well the results were reconstructed. Now, apart from that, the last 5 tracks are actually the reconstructor input logs that you get for each of the equations that you added to your model. So in here, there's a density log, there's a neutron, sonic, volumetric cross section, a gamma ray, and then it's showing also a input confidence color. So the yellow color that you see in here is actually the confidence value that we added to that particular log. It's plus or minus the value that we added to it. So if you remember, for the density, it was a 0.0 plus or minus 0.02. So in here it's actually showing us that with the yellow shading. And it also shows us the reconstructed log, which is the red curve that you see in there, and the black is the raw log. So ideally, when you look at the reconstructor curves, you want to look for a correlation and see if there's a difference between the logs or not that were calculated for that in that particular track. Now, there could be the case that one mineral model that you have built, it doesn't really cover or describe the formation that is present in a well. So for example, it could be that you have a carbonate interval, or you have a clastic interval, or even if you have a bad hole interval. Now, it could be the case that if you just build one model to all of them, it won't really capture what is present, because what that's going to do is actually going to add noise to the process. So in that case, what we recommend to do is actually build multiple models for a specific formations or for a specific conditions. So you could build one for your clastic formation or for your clastic interval. And in here, you could notice that how it has the sand, is the clay, there's some pyrite in there, and then the fluids, which is the oil and the water, and then the equations for that, density, neutron, sonic, and the gamma ray. Yeah, apart from having those equations, there's always going to be what we call a unity equation. And what the unity equation is going to do is actually going to add up all the volumes to 1. So you will notice that in all the models that we'll build, there's going to be a unity equation. And then this is another model for a bad hole, representing a bad hole interval, where it has the sand, the clay, and the fluids. And then again, it has the unity equation, and then neutron, sonic, and gamma ray, and it doesn't have a density because the density log it doesn't read well in this bad hole zone. So it could be the case that you might want to build more than one mineral model, and then you could use a combined routine that we have inside the model to actually combine those and have your clastic interval, then your carbonate interval, and the final model will have that combined model. And this is what you see in here. So once you combine those models, you could specify where do you want to have your carbonate model, or where you want to have your shell model or your clastic model. So in this particular example, we have built 3 different models. One carbonate, you can see in there. There's a shell, you can see the course in there. And then there's an anhydride model where you can see the green color there. And then the combined model will actually have those 3, but you'll notice that in here on the top interval, we have used one specific one. So instead of using all of them, we just specified so that it uses the shell shell model. And here we have used the anhydride model. In here we have used the shell model. And in here we have used a carbonate and an anhydride. So you could use the combined results routine to actually combine your models and have one single combined result. You could also integrate more data to your model. I've shown you how to just add a basic model and then just add the logs and the minerals. But if you have more information, you could also add that information to the model itself. So you could add constant equations. For example, if you have any NMR data, we know that NMR read the fluids. So if you don't want to calculate the porosity within the model, but you just want to constrain your model using the NMR data, then you could add it now to the equation as a constant. And you could see here how you could add different constants to it. You could also add a thin bed model. So if you're dealing with a laminator structure or disperse, there is using a constant, you could use those thin beds models, or even just the core data. So if you have a porosity of core and you want to constrain your model to core porosity, you can use a constant and then add that curve. In this case is the porosity from the core. It's just like the NMR porosity. And then the results are going to be computed where only that porosity exists. So this is an example on how it will look if you actually constrain your model to a porosity core data. And you could see here that the neutron has a poor reconstruction in some areas. Right over here, you could see specifically on this interval. Now, it is up to the user to decide on how to improve this. So you could do things like adjust the mineral endpoints, or if you want to adjust the zonal parameters or change minerals, or you could change the invasion factor and maybe add the saturation fluids to the model, assuming that the neutron is reading deeper than the density. You could go back and then change the neutron uncertainty, or just simply remove the neutron from the tool. And once the parameter has been optimized to get the best match to the core data, you could just simply switch off the constraint and then run the model again, and which is what you see here, that we have now a complete model with a complete interval showing us that constraint on the porosity. Mineral solver can also be run in 3D Petrophysics. So if you're not aware of what the 3D Petrophysics is, it's actually a module that we have inside IP that enables the simultaneous interpretation of multiple wells and is used to review and refine previous interpretations, allowing a consistency selection of the parameters. It is under the interpretation menu, and then you'll notice that in there there's an option for a mineral solver. So an example could be that, let's say for example you have actually run the mineral solver in a key well, and then you want to use that key well to then actually propagate the results to the rest of the wells. So you could do that with the 3D Petrophysics. You could set up the module so that it uses a reference well or a key well, and then distribute those modules to the rest of the wells. So you could also distribute the parameters, the model that you have built to that particular key well. Once the model is run, you could then review and edit the models from all the wells. So in here, looking at this image, you'll notice that we have the minerals on the right side, and then the equations type on the left side, right over here, which is kind of like looks similar to the standalone mineral solver application. But in here, you're looking at for all the wells, and then you could add or replace the model in other wells, or you could replace this model in different wells or missing wells that don't have this model. And then you could toggle between each of the wells. So in here, we're looking at a well number 3 that has a model with the dolomite cores, clay, and then the fluids, the water and the oil. And then it's using the equation types as the density, neutron, sonic, and the gamma ray. So it's just a simple model built on this well that you could then run it and then propagate to the rest of the wells. And you could also review and edit the mineral endpoints by well. So in this particular example, we're looking at the clay parameter for all the wells, not just for one well, but for all the wells. So it's the key wells that we have here, well number 3, 35, well 37, 38, 39, and 40. And then you look in that individual parameter as the clay and the endpoints for each one of them at each well. And then you could edit it or review those parameters if you want. 3D Petrophysics also has the multi-well interactive exploit, where when you're picking your endpoints, you could use this interactive crossplot to move your dolomite points or your quartz points, of your quartz points. So you could do that for all your wells in a multi-well mode rather than just go one by one. And there's also the way to look these parameters in a 3D view and then see how that parameter actually is alongside all of your field. In summary, mineral solver is a non-deterministic solution or a probabilistic approach. It solves for porosity, water saturation, and mineralogy. It has the pre-processing calculation. You could build a mineral model with minerals, equations, endpoints. You could build multiple models to account for the difference in lithology. And you could integrate different data to constrain your model. And lastly, the mineral solver can be run with the 3D petrophysics to do a multi-well interpretation. Now let's look at the curve prediction modules in IP. This will include the multilinear regression methodology, Fuji logic, neural network, principal components, and then DTA. The IP curve prediction modules in IP is an advanced license, which includes separate modules, as I mentioned. It includes the multilinear regression, the Fuji logic, neural network, and the principal component. And these are some sort of the outputs that we get from those modules. IP also has a DTA module. It's called domain transfer analysis, which is a separate license module and what we call a premium curve prediction module. All the modules can be used for the same application, and they all have a similar user interface for user use. I'll be talking about each of the methods more in detail in the upcoming slides. So there are different scenarios of why you want to use curve prediction modules. Say, for example, what if you want to replace complex petrophysics workflow? An example could be if you want to predict a density log or a sonic log or a phase shift log, along with the curves to predict from. For example, a petrophysical results or core data or raw logs. What if you want to predict missing data from wells, right? So you could, for example, predict a shear sonic from any of the electrical logs using the wells that have that shear sonic and then apply it in the wells that have a gamma ray, a density, and neutron. What if you want to actually replace bad quality data? So an example could be if you want to predict a density log from the electrical logs using the good hole data and then apply it in a bad hole. But what if you also want to complete a continuous database on limited discrete data? So for example, if you want to predict either permeability, right, from the porosity or the volume of clay using core data and then applying in all the wells. Or another example could be if you want to actually predict electrophases from the electrical logs, from the gamma ray, from the density, from the PF or the sonic, using a core phases and then apply it in all the wells. You could do this with the curve prediction modules. This allows you to tackle these scenarios. The data selection for all of them is the same. So as I mentioned, they'll have the same interface for easy use. So this is how the Fuji logic will look. and then in here, the example is for a we're predicting a permeability from the core, and then apart from that, we're using the gamma rate, the density log, the neutron, the sonic log, and this is how the interface will look for all of them. Now, what you could do is actually save a model, and let's say, for example, in the Fuji Logic module, to then save it, and then if you go into the multilinear regression, you could then load that particular a model that you have built in Fuji Logic by clicking on Load Model. So the models can be shareable between all of the curve prediction modules. Just simply selecting the well, selecting the logs, and then specified the depths for the model build and the model run. You could also apply discriminators if it's required. So for example, if you want to discriminate a curve based on a value, you could do that under the discriminator tab. So now let me start talking about the different methods that we have available and the methodology behind. One of them is the multilinear regression, multiple linear regression. It is used to predict a result curve from a number of inputs curve. It uses a least square regression routine, which will try to find the best fit to the input data. So it is based on our R2 value. So once you run the module, it will give you an R2, and then you could base that and see how the R2 value represents the data, right? So the higher the value, the R2, the better. And then apart from that, it also gives you normalized coefficient that is part of the output as well. And this will show you the relative contribution of each input log. Again, if you'll notice, the interface is the same as the previous slide, but in this case, now the multilinear regression. You come in here, select your wells, select the curve to predict. So again, we still, this example that I'm going to be showing is actually the prediction of core permeability using electrical logs. So we add the curve to predict, and then as well as the input curve, so the density, the neutron, the gamma rate, and the neutron. Because the model is linear, it's going to save a formula, and then you could then copy that formula to then pass it on, let's say, for example, to the rest of your engineers, if this is the case that you actually predict in permeability. And then once you copy a formula, this is the output that you get. It's the permeability formula using core data and logs. Once the model is run, you could then apply the formula to the rest of the wells that were selected. And because this is a linear formula, it can predict outside of the range of the curve to predict. There could be the case that you might want to clip the horizontal curve. So if you're looking at the core permeability, a cross plot of the core permeability versus the calculated one, there could be that there's some outliers, which is what you see here. And then you could just clip those resultant curves to don't account for the outliers that you see. So ideally, you want to see a positive regression, right? A positive regression of that calculation that you did. Fuji Logic is another curve prediction module that allows the prediction of a resultant curve from a number of input curves. Now, the best way to explain this is to actually have a look at a daily example. Now, let's take a look at the statement, today is sunny, right? We said that today is sunny if it's 100% true, if there are no clouds, right, in the sky. This statement is 80% true if there are actually clouds, a few clouds in the sky. It is 50% true if it's a bit hazy outside, but we could say that this is 0% true if it rains all day. And then we could say that today is definitely not sunny. Okay, so what the Fuji Logic does is a mathematics of the probabilities. Okay, it assigns the probability to the quality of the prediction that's been done, and it recognizes more than just a simple true or false value. So we use the the methodology from Steve Curry, and it's an application. It is a paper that he brought on the applications of the mathematics of Fuji logic to petrophysics. So if you're interested to actually have a look at more in detail, I recommend you go and read this paper. But it's purely based on the mathematics of the probabilities, like I mentioned. There's two basic modes that you could predict with the Fuji logic. So you could predict lithofacies and permeability. Now these two are important for when you're trying to understand the sedimentological controls on the reservoir quality distribution, as well as when you're actually building your input to the 3D modeling. If you want to actually predict a fixed value, that will be the facies. But if you want to predict continuous, that will be things like log curves or core permeability. This module cannot predict beyond the range of the curves to predict, and it's purely based on the mean and the standard deviation of all the data. For facies model build, Fuji logic categorized the input curves by grouping or binning the curve to predict. In this case, will be the facies. So you choose the number of bins into which the training data is to be divided. And what IP is going to do is actually try to sort the training data into roughly equal sample bins. It starts from the lowest value and extended it all the way to the highest value of that input curve. And then for each data bin, IP calculate the means and the standard deviation. And this is actually what you see represented here on the cross plot. So this particular example, facies calculation, it has 6 different facies, and you can see the bin numbers here, 1, 2, 3, 4, 5, and 6. And then you will see that it also represents, it has a gamma ray value for it, because it's one of the inputs that we use as to build the model. And it'll show us the low value and the high value. So gamma ray ranging from 0 to 200, as well as the neutron log. So you can see all the 6 bin numbers, 1, 2, 3, 4, 5, and 6, and then the low values and the high values for the neutron. Same thing for the density. Now you also see that there's some bars alongside, and these bars actually represent the standard and the mean deviation for that particular facies. So this will be the low value and the high value of the standard deviation, and then the red line across is actually the mean value. So if we're looking at a facies number 6 for the gamma ray log, we could see here that the ranges goes from 50 to 100, if we're talking like log values, and then the mean value will be around 75 for that particular facies. So you could see the range from the low to the high values. And ideally, what you want to look for is actually a trend. How are the data is looking with this 6 bins? It could be the case that maybe 6 bins is not enough, and we might want to actually decrease or lower that number. You could also use the histograms for that, to do that, to see how the data ranges for each particular facies and each particular log. So in here, if we're looking at the gamma ray log, you could see it, how it ranges from the low to the high, and then the blue line that you see here is actually the mean value, and the standard deviation is being represented by these green colors. Fuji logic can also be used to calculate permeability. So as we know, the permeability is a very difficult rock parameter to measure directly from electrical logs, because it is related more to the aperture of the pore throat rather than the pore size. And determine permeability from logs is further complicated by the problem of the scale, right? You could be that many wet logs have a vertical resolution of typically 2 feet compared to the 2 inches of the core plaque. So when you add these problems together, it is surprising that predictions can actually be made at all. But the Fuji logic tackles this problem. The mathematics of this provides a way of not only dealing with the errors, but also using them to improve the prediction. So in here, we have done a permeability prediction where there is a part of the input logs is the porosity and the volume of clay. And again, you will see that data has been bin or grouped in different numbers. So for permeability, the default value is 10, but there's nothing that's stopping you to actually increase or lower that value. And you can see how actually the data range is there. And same as the previous slide, the colors here represent, the green bars represent the standard deviation values, the low and high, and then the red bar represents the mean value. So the data is divided into equal sample bins, and then statistics are going to be run for each bin that you have divided that data. There's still a sample of permeability. So just when you're actually looking at the plots, at the log plot from left to right, you see the logs that you use as an input, and then in here there's a comparison of how the core permeability look and how the calculated one looks. And it shows, so in this track, it shows the most likely result and the second most likely result, which at the end, because we're dealing with probabilities, it shows you the result with the highest probability and the second highest probability. Apart from that, it also shows you a closest of fit, which is the curve that you see in here, and that provides an indication of how good the results are. And so you could just, what the closest of fitness does is it compares the result to the original curve that it was used in the model. And then you could see the difference between the predictor curve and the core one. And this is the same data, but in a different scale. Neural network is another curve prediction module, and it uses backpropagation learning technique. It does this by training the data, which is actually different from the previous module that I have shown you. In this case, you will have to train the data that you actually add into the model. And it does this by actually selecting the intervals of where you want to train this data. So ideally, you might want to start for small intervals. And once you pick those small intervals, then you could see if they actually represent a rock type or a geology or a facies. This module can predict beyond the range of the curve to predict, but because it's a learning technique, you could, every time you run the module, you get a different result. And sometimes we could overtrain the model, and we wouldn't know when to stop. So it's a bit difficult to know where exactly can we stop so that we don't overtrain the model, because there's always a better model there somewhere. You can use it to calculate permeability. So again, we're same example where we're calculating permeability from core and the logs, and then you can see them in there. You'll notice that the setup is the same. You just add the wells, and then as I mentioned, you could also do it on a multi-well mode, so you could start adding more wells to the model. But the difference here is now has what we call a training zones. And this is how you're training your data. You could do it via interactively from the plot directly. And there's some sort of like parameters that you could tweak on the training settings. So when you look at the plot, you could interactively create those training zones. Notice that for this one, we have actually created the zones to represent and capture the data that is coming from the core data. So in this interval right here on the top, and then this interval here on the bottom. And then once you pick your zones, you could then train the neural network, and it will give you a comparison track showing how the core permeability look and the predicted permeability, which is the red curve that you see in there. It also has the closest of fit, which is the structure you see in here. And again, this provide an indication on how good the results are compared to the original and then the resultant curve. Principal component analysis is another technique that we have available for the curve prediction license. And This is a technique that can be useful in petrophysics. If you want to do a preliminary method of combining multiple logs into a single or two logs without losing any information. So what it does, it reduces multidimensional data to lower dimensions. So in here you could see how we have used different logs, neutron, sonic, gamma ray, to come up with a 4 different principal components curve. What this does, it reduces the multidimensional data set to a lower dimensions for analysis. It could be used on a multi-well mode as well, and you can use it for correlation or phase analysis or any regression analysis if you want to do. Now the data that's been added into the model, it's normalized for each curve, and the normalized data is then used to then create those curves that you see here: PC1, PC2, PC3, and PC4. In this example, once the module was run, it gives the eigenvector, right? And the eigenvector shows the percentage of variability for those logs that were used in the model. So we're still using the same logs, density, neutron, sonic, and gamma ray. And you can see that PC number 1 actually has the highest percentage of variability, which is a 58.56. And principal component 2 has the second one, which is a 34.26. And the previous slides, you saw how on the what's new in 2019, you'll notice how I show you how these eigenvectors can actually be represented graphically with the cross plots. Domain transfer analysis, it's a module exclusive to IP, and it uses n-dimensional partial differential equations to determine a mathematical model of the relationships between a set of input and the data to be predicted. It was developed to tackle the problem of predicting petrophysical or geological properties from minimal data. It's based on a partial differential equations, and this contains unknown multiple variable functions and their derivatives. So if we look at the partial differential equations, what it does on the initial state, so for example, if you're calculating y, you're using inputs like the x1, x2, x3, x4, and x5, and it's using actually looking at all the relationships between all the logs that you're using as an input to then calculate y. So it's using x1, the relationship between x1 to y, x4 to x2, x5 to x2. So it's a representation of the interaction between all the elements that actually been used on the model. And then at the final state, the interaction between the various elements has been resolved. So rather than just looking at all the points, now it just look at a specific direct various elements that actually were resolved when it's actually running the module. So you can see now that it shows you the relationship between x1 to x2, x2 to y, x4 to x3. And it builds the relationship between the input curve and the curves that actually were added to predict. DTA does not mix the input data, and this is a difference from the previous modules that I actually show you compared to multilinear regression, Fuji logic, and neural network. So the data is actually preserved. All the data is preserved. Now, LR actually presented a paper with this methodology last year in the SPLWLA, and there's actually a paper for this. It's called Domain Transfer Analysis, which is a robust method for petrophysical analysis. And the paper goes into detail on how DTA can be compared versus the other methods, and using different scenarios and application, and how to best handle the variety of the dynamic ranges present in the petrophysical input data. You could use this as a way to predict, let's say, for example, water saturation or permeability, or if you want to predict discrete or continuous data. You could also use it if you want to compare wet logs to assess similarity in them, or if you want to do any well log repair due to a bad hull condition, or if you want to do some sort of like reservoir rock classification. So one of the examples that they actually presented in the paper was this, and is a gamma ray prediction. The same inputs was used for all the methods, and it validates the effectiveness of the DTA. So you can see how DTA was compared to the FujiLogic method, and the black one is actually the DTA gamma ray, and the FujiLogic was the red one. And then it also shows a comparison from the PCA principal component versus the DTA. And then you can see which one gives you a better output. So in this case, it was DTA. There's also another paper that's actually been presented this week, actually in Abu Dhabi, and is during ADIPEC. And this is, again, is using DTA as in automated selection of inputs for log prediction modules using the DTA modules. And this was an R&D project that describes the new techniques for optimizing input selection prior to model build. So the selection tool that selects the most appropriate input parameters can be used to do a machine learning model. And you can enter a large amount of curves, and from those it ranks each curve. And you can then decide based on that which curves to use in the predictor model. So this is the experiment eye, and then you can see how the logs have been displayed there, and then see which, and then you could run the logs that were added part of the model. So the last module that I'll be talking about in this section is the image analysis module. Before I actually dive into the module functionality, I thought that it would be worth just to have a look on how borehole images can help to fill the gap between the core data and the seismic data. So, you know, whenever we looking at the core data, it could be that there are some limitations in the coverage, right? Or whenever we're looking at the 3D seismic, we'll notice that it could be a limitation on the resolution itself. So what's in between the seismic and the core is the borehole images. And this is where they are important, because they capture the coverage that has a limitation on the core, and the resolution that has a limitation on the seismic data. And then looking at the borehole images, it's really powerful when it comes on if you want to look for geological features or any, let's say, for example, channels or unconformities, or if there's any fracture identification that you want to do, or any ripples identification by observation. So the borehole image will give you that. Image data is acquired normally by tools that had a set of pads or rotating sensors, and this is what you see here. This is one of the image tools, and they're conveyed by either wireline or a logging while drilling, LWD. And some of the tools can be restricted to a mud type or a hole size or a convergence technology. IP can handle all industry standards image analysis tools. We have predefined templates that you can choose from to manage the image data, and you can also choose templates with naming convention that are actually coming from other software companies. So in here, you can see how we have listed all the LWD tools. That includes a azimuthal gamma ray, azimuthal density, azimuthal microresistivity, or electromagnetic propagation. And you can see all the tools available that we have in the module for all the service company. Now for wireline tools, because there's more, you see more options listed here. And these are the electrical microresistivity imagers and acoustic images. And then you'll see them how they're actually listed there by company. So we have the Schlumberger tools for the wireline Schlumberger tools, the Halliburton tools, the Baker tools. So it's really a complete list of image tools that are available in the market. In IP, we have 2 different modules that allow you to do the analysis. So there is the basic method that allows you to display the data and then just do a simple basic depicking. This is part of the basic license. But we have a module for it, and it's called the image analysis module. And this allows you to do a complete process of the data, of the raw data. So you could apply corrections, you could do a structure analysis, you could display different plots to look at the dip plots. And this is something that the basic license doesn't give you. So to summarize the main functionality, with the image analysis module, you could load the data, you could create image tools, you could do a data display either on a wellbore cross-section or in log plots, which is what you see in here. You could apply corrections available. So there's a speed correction, strike correction, or the bottom offset corrections. You could then do pick the features from the image that has been corrected. And we do have the auto and the manual way to do it. And then once you pick those features, you could then categorize or define those picks. Things like bed boundaries or fractures, if you picked any fractures. And then once you pick those, you could then do a deep analysis using different plots that we have available. And you later will see what are the plots that we have available. And then apart from that, you could also import or export the picks and then do a fracture analysis calculation or a fracture aperture. And then lastly, a 3D visualization, which is what you see in here. So I mentioned about the corrections, and in here you could see all the corrections that we have available that you could apply to the raw data when you're processing these logs. We have a variety of image tool corrections like the accelerometer correction, or in other words, like the speed correction, and this corrects the tool speed based on the accelerometer data. You could fill gaps to your data, and what it does, it removes any gaps that are present in the source data. Or you could do a center reprojection borehole correction, and what this does, it reprojects the tool to the center of the borehole. Or you could do a straight correction, what it does, it just simply reduces the vertical striking by equalizing the path and the bottom values. And if there's any fixing depth and misbehaving buttons, this strike will correct for it. As well as those corrections, you will see that there is an image deconvolution, image filtering, and an image flattening. And I'll talk about those more in the upcoming slides, because I'll be showing you some examples. So some of the examples when you apply the center reprojection correction. So here is an XRMI from Halliburton, and you can see on the left image how on the left cross plot you can see how the raw image look that is being that is not center. And then in here on the right side, we see a corrected image that it has applied a rotation to the image after the correction has been done. And you can see how now the tool actually being center reprojected. Now this correction is normally required for when you're dealing with centralized tool, the non-centralized tool that has an independent arms, like in this case, the Halliburton XRMI, which is what you see in there. The image deconvolution correction, it's a way for deconvolute an image. So as we know, borehole images could be noisy things, right? They could suffer from tool stick or borehole effects, or also things like a gas effect or mass effect or a bad pad contact. So the image deconvolution will correct for those and allows to reduce the noise by deconvolute an image into what we call a low frequency images, which is what you see in this track, and a high frequency images, which is what you see in this last track. And then what the image that is on track number 1 is actually the raw data. So once the deconvolution has been applied, once the correction has been applied, looking at the low frequency images, you could see that there is a better view for the lithology or the facies, right? So in here we're seeing a facies on that. And the high frequency images correspond to mostly features like fractures. And you could see here how we could see a fracture on the high frequency image that we cannot see on the low frequency image. Image filter is another correction that we have available, and it is also called convolution or transform. And what it does, it actually enhances the filter methods that we have on the images. So in here we have an FMI, a static image on the left that has been enhanced by applying the Laplacian of Gaussian method, which is one of the options that you see on the filtering options. And what it does, it just simplifies areas of a rapid changes in the images, and you can see how the corrected one looks like on the right side, and where you are able to see the features better, the cross bits better, that rather than look at it on the left side. Image flattening, I mentioned something about this when I show you the what's new in IP 2019, but just to highlight, it's a technique that is used to remove the effect of borehole inclination and the deep impact from a borehole image. And I briefly talk you guys about this example. It's the same example that I show in the what's new in IP 2019, where we're showing a speed corrected image and a pixel detailing the regional dips. And then in here, you could see the flattened image using that data that is available. So the required inputs for a flattening correction is that you will need an image tool, ideally a one that is corrected, a corrected image, and a pixel of the structural dips. So apart from consider to apply the correction to the images, you may also consider fixing any curves that were acquired incorrectly. And this could be curves like the navigation data, inclinometer data. So that'll give you accelerometer and magnetometer data. And we have a module called a navigation to QC that allows you to correct these curves. And you can repair the accelerometer and the magnetometer data. We have different series of output parameters that you could apply. If you want to add any discriminators, you could apply that as well. If you want to use the whole survey, you could add that as well. Or if you want to apply any filters, then you could do that as well. So there's different parameters that you could trigger. And then ideally, when you're looking at this data on a cross plot, what you're looking after is actually to see a smooth sinusoidal response. In case there's not a smooth response, what you could do is actually use this cross and then move it interactively to adjust it to the middle so that it corrects the data. Or you could look at the logs itself on a log plot and then see how they look after they've been corrected. So for this particular example, we have a really good correlation on the data, and there was a need to actually do a correction to the accelerometer and the magnetometer, and you could see that being displayed here. So it's the accelerometer on the first track and the magnetometer on the second track, as well as the navigation data. So you have your deviation, your azimuth, and your relative bearing. So it just simply reduces noises and irregular movement in the inclinometer curves. So once you have an image that's been corrected, then you should be able to see a smooth image to then start doing the picking. So this is what you should see. We have a static and a dynamic image. And in IP, we have different methods to do a depicking. So you could either do a manual way or an automatic mode. So if you're doing a manual way, there's an option on the log plot that you could make available to then start actually picking those picks. So there's different methods. So you could pick from a simple method, from a trace method, a point method, and you could just go on the image and then hover your mouse on where you think there is a pick, and then create a sinusoid from it, and it will give you a dip, an azimuth, and a tadpole for that, which is what you see in here. So there are different data types, and you could see them listed in here. So if you're picking a cross bed, you will choose a cross bed option, bed boundaries, or fractures, or any bedding or any planar bedding. You will just come in here, select the dip, and then select the data type for that particular dip that you pick manually. You could also pick breakouts from the images, and that we treat them as perpendicular vectors. So there is an option on the options to select from if you actually want to pick a breakout from the image, and you can see that represented in here. So it's a matter of just coming into the image and then select that. Or if you want to represent it a whole, which is what you see in there, or even just a trace, then you will use that method to account for a trace pick. And then once you make that pick, it'll give you a tadpole showing you the dip and the azimuth. There is also the automatic picking feature. So from the image itself, you could right click on it, and this will auto dip generation. You right click on it, and you'll have an auto dip generation option, which is this window that you see in here. And then you will have to just select the type of dips that you want to create from, and the density of those dips that you want to create. Once you pick your dips, you could then display them on plots. So we have many different plots that you could display these dips on. So there's a sinusoid over the image, there's a tadpole in a dip track, there's a stick plots, or you could also display it on a spreadsheet, and many more plots in here that you could see that we have available. I'll just give you some briefing on the plots that I just mentioned. So for example, here we're looking at Rose diagrams, and they're useful when you're actually analyzing the data containing the amount of the direction values. So for example, you want to do a paleo current analysis to see the orientation of the joints, if there's any joints or the beds. So you see them in there, the three different plots. There's a Rose plot, the dip azimuth plot, and the modified dip azimuth plot. And you can see the dips being displayed on those particular plots. There's also the cumulative plots, and that's just purely displaying the depth versus the cumulative dip angle, and the depth versus the deep angle difference. Stereo nets are also available, and that's what you see displayed in here. This is purely a deep analysis plot to help understand the relationship of the deeps to a well or a field. So in case you actually want to have a better understanding on the tectonics. Walkout plots are also available in IP, and they allow you to display the dips and then be plotted nose to tail to help find trends and actually facilitate the interpretation of for the dips that you have picked. So in here we're looking at a dip azimuth one, where we're looking at the vectors are actually drawn from the nose to the tail using the dip azimuths. In here we're looking at the dip angle, and the vectors are drawn from the nose to the tail. So in here we could see where's the deepest section, and in here we could see where's the shallowest section going from east to west, from east to west, going from shallow to deeper. And then there's the directional dip angle plot and the 3D dip angle dip azimuth plot. The module inside IP also has an option for fracture analysis. Just to briefly talk about what is a fracture. So it's a simple failure plane cutting rock matrix, right? And they form in different orientations, which are related to the earth stress at the time of fracturing. So there's different types. You have the natural fracture, the induced fracture, joint fracture, fault, and in IP we actually have an option for that you could actually select the type of fracture that you're dealing with. And if there's a case that we don't have the data type, for example, if we don't have a natural fracture data type, that you could actually edit the customized table and then add that natural fracture to it. So when you're picking the natural fracture, then you have a data type for that one. And picking these fractures are pretty simple. On the log plot, you could just hover your mouse, and then again using the manual deeping using the manual deeping options that we have available. For this case, you will use a trace option so that you could actually trace the fracture alongside the image. And then once you trace it, then you get a deep and azimuth for that particular fracture. And there is a module inside IP, inside the module that allows for a fracture analysis one. And what this does, it just gives you a statistical analysis of the occurrences of the fractures that you have picked. So in here, we have picked a closed fracture, which is represented on the yellow color. There is an open fracture, which is represented on the with the red color, and there's a tension gauge, which is represented with the blue one. And then you could see actually the analysis, the statistical analysis of that, showing you that. So we use the method, the Tergassi weighting method, and this account for deviation and provide a weighted statistics. And the inputs for that, for the Terzaghi weighting, is actually the borehole azimuth and the borehole deviation with a window height. And then you could run the module and I'll give you the statistics of that particular fracture. There's also histograms available to display the data, and this is purely used when you're doing some sort of like a SAN count calculations. And you can see how that from the image you could display a histogram plot, and then that's represented here, and then select the threshold of that particular image and that particular section. And at the end, and you could then build a complete picture of the process image using the tools that I show you that we have available. So you could have your static and dynamic image, and then you could also have the pics that were actually picked from the image itself, and then you could use the mini plots functionality to actually visualize the deep plots that IP has available. And then this is just an example or how a final one will look. Now with this slide, I conclude this section. So we could have a 5-minute break before we carry on into the last section.
Cool, and then we'll come back to you, Jennifer, for the last section and Q&A. So thank you for that. Everybody, our last section of the day now is the IC introduction and overview from Jennifer, with particular focus on the integration with the IP analysis. So I'll now hand over to Jennifer, and then after that we'll go straight into the questions that we received through and try to answer those. Many thanks.
Thanks, Rich. So for this last section, we want to show you an introduction of our sister product IC, where we going to look at using IC as an advanced visualization kit for your IP wells. So for the next few minutes, I'm going to talk briefly about the main IC functionalities and how you can interrogate your IP wells and visualize those results on a map. If you're interested to have a look at more in-depth at our IC product, you could get in touch with the GeoEnergy team to schedule a more in-depth section. What is IC? So IC is our sister product that began its life 15 years ago as a product called ODM. Since then, we have worked with our clients to improve on the workflows and the toolkits that are available. It's a powerful tool if you want to do integration or visualization on understanding of your well data, and you will see how this can be done in the upcoming slides. So IC, like IP, it can be used through the life of a well. You could use it from the exploration, appraisal, development, production, and abandonment. And you can incorporate any well-based data, things like logs, tops, zones. It is a module base, depending on what you want to use it for. So we have the IC platform that allows you to do things like data management or transfer data, or if you want to use any of the QC tools to QC your database. It also has the IC geology part for data visualization. It has the IC stratigraphy if you want to do a stratigraphic awareness. It also has a data links option that allows you to connect to different products like OpenSpirit or even IP. And it also has an RPM module for reservoir performance and allows you to do a monitor of time-based data, like your production data. And then lastly, it has an IP compatibility, which is what I'm going to be focused on this section, as I know that the audience today are petrophysicists. Integrating data with IC is easy. So if you look at IC from the database management, you can store data like logs, peaks, intervals, images, and surfaces, GIS, and getting data in and out, it's pretty simple as well. This can be done by either using the direct links that we have available, or you could do it as a way of importing and exporting files. So if you want to export LAS files or ASCII files, or even grading or polygons fault files or shape files. You could also use IC to reference to a file location. So if in your database you want to actually reference some external images or some of a spreadsheet, so you could reference to that file location. And there is also, like I mentioned, a compatibility with IP, where it has either a direct link or you could do a simple synchronization of the data. I mentioned how IC has a compatibility option with IP. So when you're actually using both products, you could synchronize IP with IC, or vice versa. You could synchronize IC with IP. So, for example, you could be using IP for a porosity and water saturation calculation, and then you could then use IC to do the data integration or to visualize the data that actually you brought in for IP. it is a standalone application, but you could also access those tools when within IP. So in here, in IP, if you go under the advanced interpretation, there is an option for IC correlation mapping. If you click on it, it will actually use an IC license, and it will take you directly to the synchronization window, where you could pick what is the data that you want to synchronize from the two products. So you could synchronize data like well header attributes, coordinate systems, or IP curves or IP sets. And once the synchronization is done, then between the two products, then it creates an SQL local database. So why do you want to use IC with IP? It could be that you want to improve your data management, or you want to improve your regional exploration and appraisal evaluation, or you just want to do a reservoir characterization study, or just a simple field production and LTO studies. IC uses a clean interface to enhance the understanding of the complex data and provide a clear vision of your assets. Visualizing the data in QC, it's pretty straightforward, and I'm going to show you how that can be done by creating this 2D maps, and it also has an option to create a 3D maps. There's also has an option to build correlations and create surfaces. So there is a lot of functionality that you could that IC has that you could do with the data that actually has been brought for IP. And I just thought of like showing you some of the examples of IC displays. So in here, you could see a 2D map on a multi-well. It's showing a multi-well, and it's also showing some well sticks that showing the gamma ray log and the formation for each of the wells that's been displayed on the 2D map. You could also build simple correlations. So the example here is showing a simple correlation based on a well map, and showing interpreted formation intervals between the wells. So the colors that you see here are actually the formations. There's also, you could build 2D maps using surfaces as well, which is what you see in there. So there's actually no limit to what can be displayed on this chart. And this is the power of IC visualization and the integration with the IP analysis that you have done, that you could actually visualize that data and then see if there's any correlation, see if there's any changes. And you see that once I show you the software. And this is just another slide showing more examples of it. So in here, we're looking at a 2D map. In this case, we're using surfaces and greetings, and it's also using queries within that map to query the wells that are on the map. So the red color here actually shows an average value of a gamma ray curve in a particular formation. So you can see which of those wells that have that red color has that gamma ray value. It's also showing analysis sticks in here, which is the bar that you see there, and the green color represents the lag on the positional environment, while the yellow color represents the proximal lowers north phase, and the blue one represents where is the transition zone. So you could actually display that alongside the wells. There's also a way for you to create a 3D maps, which is what you see in here with the surfaces being displayed, and you could add formation tabs to the map, and then the wells, and then the surfaces. So now let's have a look at a quick demo in action with data that is actually coming from IP. Now just bear with me for a minute here, because I need to switch now into the software. Okay, so by now you should be able to see the IC software and on the display.
Yes, we can see that, Jennifer.
Thank you, Rich. So this is our IC software, and it has been designed in a way so that it's easy to navigate. The main menus will have ribbons that correspond to each model. So if you're loading data, you will know that you will go into the import and export tab. If you're building maps, you know that you will go under the maps tab, and in there we have different functionality. The same thing goes for if you're building charts or if you're dealing on a project base or wells. So it is made in a way so that it's user-friendly. This data set has been loaded and shared with IP. So you can see the IP wells here. And alongside, it also shows the data that actually was brought in apart from the wells. So you'll see that there is some well header information, the positional phases, and it also has the IP set water saturation parameters and the IP tops, the IP peaks, as well as the lithostratigraphy data, log data, rock types, and then you could see that alongside on the database browser. So once the data has been brought in, then you could start creating and use the visualization tools that we have available for that. And one of those is the map. You could create a 2D maps, which is what you see in here. So in IC, our base map here is showing us the well that actually are on the database browser. We have built a map to help us visualize the spatial distribution on our data. Now within this map toolbox, we could actually then start adding layers to it. Things like queries or resources that we have available, like a GIS data or subsurfaces. And I mentioned queries because this actually help us to understand the data and we can highlight on the map and a specific criteria. These are actually easy to build and can be saved easily within the database. So for example, on this T2 map, I could start doing some basic checks. So the data that's been brought in from IP, I could start saying, okay, so which wells actually contain my IP analysis? So then I could drop that query there, and then now it shows us with a color, green color, where is the wells that have an IP analysis. You could also ask things like which wells contain my reservoir. So for this particular database, the reservoir name is Evie. So I could then build a query so that it shows me which of those wells have that, and you could see them highlighted on the map. You could also ask things like which well contain a water saturation. So I could then use that query, and now it shows the purple color highlighting the wells that have a saturation data. But you could also go more in detail and see which of my wells contain, let's say, for example, a porosity value that is greater than 0.1 in a specific formation. So in this case, I'm going to stick to my reservoir. So then that will be this one. And then now it shows you in an orange color which of those wells have it. And then you can start building a picture of your field with the data that you have available in there. Now, building these queries, they're pretty easy to do. I could just simply create a new one where I will need to pick the parameters and the investigation and the zone of interest. So in this case, I'm just going to build a simple one that has a zone of interest of my formation Hawkins, a different formation. And then I could just select the data type. So in this case, I'm going to be using the IP tops that I brought in from IP. And then once you have that, you could then click on OK. And then you'll then allow you to actually select the color that you want to display this on the map. So for this one, I'll just put a purple circle. And then before you actually create it, you could actually test it. So you could test the query, and then you notice that it brought up 12 wells that have that particular formation, Hawkins. And you could then actually use that and then use that query to then actually, sorry, it says that there is already a name built with that. So I'll just put that, I'll just add a name. And then you could use this query to then actually query that on the map itself. As I mentioned, there's more layers that you can add to it. You could also add greetings, surfaces to it. So we have an option for structural, thickness, or if you want to build a component or a lower statistics one. So in this case, we have previously created a surface with a top named EV. I could just simply drag that one and then drop it into the map. And you'll now see how that is actually being reflected there, where we can see that in this particular example, the colors actually represent where we have the high values, which is the blue ones, and the low values, which are the red values here. And you could edit those surfaces if you want. For example, if you want to add any fault polygons, you can add those manually to explain the changes that you see from going from the high values to the low values. So I could interactively right click on it, and then there's different tools available. So for this one, you could draw a polygon and then to account for a fault that might be happening between these wells, and then you could build a polygon from that path that you have created, and then assign it a name, and then you could also assign a color to it. So let me just make a red color so that it actually highlights that on the map. And you'll now see it in there. We have built a manual fault, and then we could then now explain that the changes going from the high values to the low is actually because of the fault that we have in there. And you could reshape those surfaces based on that fault. So I can then go into my properties of that top heavy that I built, and then I could add the polygon line in there, and then reshape that greeting. Okay, and now you can see the changes accounting for that fault that I just built manually. Let me just actually take it off and then go back into how it was before. Okay, now those surfaces can actually, you could build them inside IC, or you could actually bring them from an external grid. So I'm just going to show you how quick it's actually to show to build a surface. So within these maps, you have an option in there. I'll just remove this polyset that I just built. So within this map, you have an option to build a surfaces. So if I click on that option, I'll just select the area that I want to actually build that surface from. And then it'll ask you for a name. And then you could pick the surface style. So you could pick things like a structural, a surface, techniques, component, locate statistics, or GIS attribute. So I'm just going to build the locate statistics one. And in this particular one, I'm just going to use a parameter. So I could define the top and base of this particular parameter. So I'll just pick the heavy formation. I'm just going to stick to the reservoir one. And then you could then select the subtype that you want to actually create that gradient from. So in this case, there's data that I brought in from IP that has the porosity and the water saturation. So I'm just going to select the saturation, and now I want to build a grid that has an average value for the water saturation. And once you have that, you could then specify, the greeting method. So there's different options like the accretion, inverse distance. And once you pick the method, it's going to try to build that greeting based on the methods that you pick. You could also select the display of the greeting and assign a color to it. So if I want to make it green, then I could fill out that so that it actually creates the values for that particular level. And then I could then apply that. So now you can see that I have built a locate statistic one surface using an average value of my saturation. I'll actually just remove this top EV one. And then now so that you guys can see it better from your side. And then it's showing us the saturation value among all the wells that are actually being displayed on the map. Now, from within this map, you could also create correlations of your data and see and understand the structural distribution of your zones. So to do that, there is an option there called Build Correlations that if you click on it, then you could then select from the map the wells that you want to build the correlation from. So I'm just going to go from west to west, from west to east, and then I'll just build a chart from this correlation map. And then there's different options that you have to actually go through before you build the correlation. So you could specify the depths for that correlation that you're building. So I could just apply depths, or you could apply the limit, or you could just simply select a data type that you want to select the limits to. In this case, I'm just going to use my IP tabs, and then you could apply those depths to the wells, to all the wells that have been that I selected from the map. Then there's a scale option. There's also the template option. So I have already predefined a template before that I'm going to be using to display this data. And then you could also auto-type those wells using any specific formation. So I'm going to use my data type as the tops. And then you just build a chart from a map, from a 2D map. And then again, you're looking at the wells from west to east, and then you can see how this well in here is the deepest one, and this is the shallow one. And you could once you build the charts and the correlations, you could actually start aligning your wells. You could either do it manually, or you could use the options here to align your wells based on an interval base or in a specific depth or on a zero depth. So there's options to align these wells. Now the template that I used for this was, as I mentioned, was a predefined one. So if I actually zoom in more, you could see that it's using the logs, the gamma ray, and the caliper, and it also using the XRD data and the electrophases. And then it has correlated those wells using the formation tabs that I brought in from IP. Once you have this correlation, there's a lot of things that you could do from the charts. You could edit those formation tabs that actually put the wells together. So in that case, I could manually account. So for example, if I know that there could be a fault here between these two wells, then I could right click on it, and there's different options available for you to do that. So I could either reshape a tide, which is what I'm going to do, to then account for that particular fault that I see. And then I'll just add another point in there, and then you could just finish editing, and that is going to be actually reshape it based on the fault that you built. There's a slightly chain here. I could just make it more bigger. But just to carry on, once you build these correlations, you could then start adding more data to your charts. So if I want to actually add the map that I just built, the 2D map, I could just insert that map by coming into here, right click on it, and then select the map. So for example, if I want to bring in the map with that has the queries on it, I could then start adding that into my charts and then start building a broader picture of all the data that I have available. And then I could also brought in the 2D map that I have with that's showing the grids. I'm just fighting here with the resolution of my screen, sorry. And then again, you could then start making a complete bringing all the data that you have available, and then start building the story behind this. So there's a lot more that I can cover, but I just would like to stop here. And it was, like I mentioned, it was just a quick overview of some of the functionality that our sister product can do when you're actually dealing with IP data. So with that, I could open the floor for questions, Rich, right?
Yes. And we've got a couple in here, if that's okay. Now, I'm not the expert here, Jennifer, so I'll ask the question, and it's come in. What is the benefit to use density neutron sonic correction in mineral solver module? Does the question make sense?
Yeah, well, it depends on the logs that you have available. So if you have the density log and you trust those logs, then the benefit will be that you could use them and then create a robust model based on those logs. So it just depends. The benefit will come into how the logs will look, and prior to coming to the mineral solver, you could also use a sanitation technique where you could, there's a need to correct some of the logs, that you could do that prior to coming to the mineral solver. So it just purely depends of the data quality of the data that you're adding to the model.
Great, thank you. And on the same topic of mineral solver, can saturation equations be dealt inside mineral solver model?
Yes, you can add the resistivity and conductivity curves to the model, but we'll limit the user to a modified Archie equation in case you're using Archie for saturation, where M is equal to N. And like I mentioned during the presentation, the recommended way is to actually solve the equations outside of the model. But there's not a limitation. You could also add them to the model as well.
Perfect. One other question. I see scale between wells in property contour map not accurate through 3D parameters view module. Is there a reason for this? No, I don't quite know.
Well, I did show the 3D petrophysics, but I didn't see any issues with it. So I'm not really sure what they're referring to.
Yeah, what I'll do, I'll take that question offline and see if we need to get some additional detail and come back to the person that posted that question. Just to go back, can you use other curves in the input model in the new IP curve auto edit module?
Yes, you can. You can use other curves. So you could use things like compressional sonic, potassium, thorium, or from spectral gamma. But just bear in mind that if you use other curves, it doesn't actually convolve the flags in the same way. So you might want to actually twist off the convolution of the cross plots.
Superb. What are the normalized coefficient values in the multilinear regression module?
Well, the normalized coefficients give an indication of how much each input curve affects the model. So the closer the normalized coefficient value is to 0 for an input curve, the lower actually is the effect on the model build.
Great. I think the last one sort of on IP. What is the methodology used for fracture aperture?
So that's related to the, yes, it's related to the image analysis module. So we currently do a manual approach and it uses a Luty fracture aperture equation. And it uses the integrated differential conductivity associated with the fractal, as well as the multifiltrate resistivity and their RXO. So as it uses a Luty approach. And so if you want to have a more in-depth response, you could just look at the fracture aperture from electrical borehole scans.
Superb. And then last sort of two questions I've got here down is for IC. Can we, I think you may have shown this already, but can we display seismic data in IC?
You can display images of seismic lines on the chart canvas and scale your wells to see it along them or the position of seismic coverage on the maps at a chart file. You can also include seismically interpreted surfaces grid on our maps and view them in a 3D structural surfaces alongside other wells and data well paths.
Oh, great, thank you. And the last question that I have, do we have to create the maps and correlations in IC every time we want to see a new well?
No, so this is actually one of the powerful toolkits within IC that it has the ability to store templates or resources like well queries, which is what I show during the demo, so they could then use in the future.
Oh, fantastic. Great to know. Well, I think that kind of wraps up the Q&A side of it. What I'd just like to say to everybody on the call is, well, I'd like to say a big thank you to Jennifer for the time, dedication, and expertise you've shown throughout the whole webinar. It's been very informative. So I thank you very much there, Jennifer. What we'll do is if we can get a copy of, I guess, the slides, and we put that into a little ebook, we can send that on to everybody. The recording itself of the webinar we can send out as well to the people on this call, to colleagues and stakeholders. And if there's any additional questions, queries, or actually wanting to have a look further into the advanced modules, please reach out to the team at GeoEnergy. And maybe Jennifer, do you want to have one last word, and then we can maybe hand over to Mohamed as well?
Yeah, sure. Well, I know we cover a lot, and there might be certain things that we didn't cover in detail. But I just hope that this section gave you an overview on, the new features that we have on the new version and some of the advanced modules. But like you mentioned, Rich, if you have any more questions, more in-depth questions, just reach out to the GeoEnergy in case you want to schedule a more in-depth demo of the material that we covered today.
Oh, that's great. No, thank you for that. And maybe Mohamed, if you're still on the line, if you just want to maybe wrap up to the attendees, that would be fantastic.
Yes, sure. First, I want to thank Jennifer for this great effort today, and I want to thank everybody who shared some of his time with us today in this webinar. And we are happy here in GeoEnergy to receive any question or clarification by any mean via email or phone or anything. We will send it to Jennifer and our technical support team in Synergy, and we will share this information with you. Also, as Rich mentioned, that we will send the slides in PDF format along with the link for the recording webinar itself to be downloaded. And we thank you for your time today. And thank you, Rich. Thank you, Jennifer. And that's it. Okay, any if you want to close, Rich.
Great. Thank you. Thank you, everybody.